All right, so we're just gonna hop right into recitation week 5 and start going right into this. So when I read this question, a student prepares a solution from 0.15 molar formic acid and found its pH at equilibrium to be 2.48. I'm then asked to determine the Ka value. If I'm going to determine the Ka value, I need to know the concentration of the H3O plus ion or hydronium ion because I already know the concentration of my acid. So if I take the pH, I know that from the pH 2.48, if I raise that from 10 to the power of negative pH, I can get my hydronium ion concentration. So in this case, if I do that, I'm going to get 0.0033. That's going to be my concentration of my hydronium ion. Now, if I plug that into this equation, so if I say this equals this hydronium ion concentration squared, so that 0.003 squared, and then I divide that by the concentration of my acid minus the concentration of my hydronium ion, I would then be able to calculate my Ka value. So again, this is all about plugging things into your calculator. So please be sure that you're confident plugging in large equations like this into your calculator, or you're able to do quadratics, as that's going to really help you. If you are not comfortable with this, please reach out to me or reach out to our wonderful teaching staff so they will be able to help you. So when I plug all of this in, I'm going to plug it into my calculator, and what I get when I've plugged it in my calculator is 7.5 times 10 to the negative 5. Now, when you're thinking about what that means in terms of an acid, you just need to think of how large it is. If it's a large number overall, then that means that it's probably going to dissociate very easily as an acid. Or sorry, no units. It's a constant. But if it's a much smaller number, it means it's a much weaker acid and it's not going to dissociate as frequently. All right, now we're going to skip those and do those in recitation. Now, if I read this sentence, acids will have a low pH, and that is because when we think of an acid, it has a pH from 1 to 6, according to the Arrhenius model, and that means that they produce H3O plus ions, because if you think about it, when we're measuring pH, we're all about that concentration of H3O plus, or hydronium. Bases will then have a high pH, that makes sense, opposite to low, but also it's because it will have a pH between the range of 8 to 14. And according to the Arrhenius model, it's then going to produce OH minus ions in water, which makes sense because usually when we are measuring pH, the opposite of that is POH, which is the negative log of the hydroxide ion, or OH minus. All right, so now moving on to number 6. When we look at the concentration of chloride in an HCl solution with a pH of 3.21, we can literally use the same equation. And this is also going to equal the concentration of our Cl minus ion. And the reason for that is our Cl minus ion, when you think about HCl and how it breaks down, well, HCl will break down to one hydronium ion, or one H plus, they're both synonymous, and it's going to break down to that plus one chloride ion, so Cl minus. So in that case, the concentration of the hydronium ion is going to equal the concentration of the chloride ion. And so if I take 10 to the negative 3.21, I'm going to then get a concentration in my calculator of 6.17 times 10 to the negative 4. Now, that in itself, this is a 1. So that in itself means that we have a very low concentration. Now, what that means is it probably is a very strong acid. It's going to really be pretty damaging, which is what we kind of know from hydrochloric acid. But also when we're going forward, this means that there's not a lot of acid in that solution, which is probably why the pH is not so acidic as, say, 1 or 2, which is what we think of when we think of super acidic things. So again, this is going to be 6.17 times 10 to the minus 4 molar, which is going to equal not only the hydronium ion, but also it's going to equal our Cl minus. Okay, next is number 8, getting the Kb value. This is actually not as tricky as you thought, or maybe we're thinking, and that's because Ka times Kb will equal Kw, which we all know is 10 to the minus 14. And so when I get the Kb value, the first thing I'm going to do is I'm going to get my Ka value, and Ka is going to equal 10 to the minus 14 divided by, I need to put an equal sign in there, 10 to the negative 14 divided by our Kb value, which we can see from the equation is 4.4 times 10 to the minus 4. So I'm going to have you pause and quickly put that into your calculator, and hopefully you're going to get the same thing as me, which I get, plug that in, and then get 2.27 times 10 to the negative 11, which makes sense because when I look at my exponentials, they should be equating to just one above. So 4 plus 11 is 15, which one above, or one below that, sorry, is 10 to the negative 15, and then one below that's 10 to the negative 14. So again, this is 2.27 times 10 to the negative 11 molar, or sorry, this is a Ka value, so there's no units. Good catch by myself. All right, and then I know I have a pH of something, which we're going to get, and we first would like to see what the concentration of our hydronium ion is, and we know that to be our methylamine, which is going to be our acid, so that is going to be 0.2, and so I'm just going to plug this in. And so what I know is that I have this value, this 2.27 value, is going to equal my x squared, because I don't know the pH, right? So if I don't know the pH, then you can assume that that is x, and in this case x squared. So I have this equals x squared, all divided by the concentration of the acid, which is 0.2, minus x. Now, I'm going to multiply this side by my denominator to get them to cancel. And I'm first going to make this a bit more room here because I'm going to need more space. A little bit out of the way. And when I multiply these two sides together, I'm then going to get a large quadratic. So if I multiply that through, I'm then going to get 4.54 times 10 to the negative 12, which makes sense. 2.27 times 10 to the negative 11 times 2 would be 4.54 times 10 to the negative 12. I'm then going to get negative x times this times sign 2.27 times 10 to the negative 11. And that's all going to equal x squared. There's a bit of a lag. And that overall is going to be my quadratic. So then I'm going to move all this over here and set it to 0. And then what I get is my x is going to equal, and I plug all of that in, and I get my x equals 2.13 times 10 to the negative 6. Oops, my 3 did not come out in that. 2.13 times 10 to the negative 6, which again is going to be my concentration of my hydronium. So then I know that I take the negative log of that. So the negative log of this number is going to give me my pH. So when I take the negative log of my 2.13 times 10 to the negative 6, again, my 3's just don't make it. All right, 2.3 times 10 to the negative 6. Ooh, this is all not coming out very well, is it? And my 10 is horrific. 10 to the negative 6. I then get a value of 5.67. All right, there we go. Oh, my 6's again. 5.67. So that's going to be my pH. All right, moving on. So, what is the pH of a 0.35 molar calcium hydroxide solution? It says show your work. Okay, so when we're thinking about the pH of something that's a base, we now have to work backwards. So instead, if we find this concentration, we're actually finding the pOH first. And in this case, we've actually got 2 hydroxide ions. So all I've got to do is break this down. I know I have 2 hydroxide ions to every calcium dihydroxyl. And so that just means that I just take this concentration and multiply it by 2. So if I multiply that by 2, I'm going to get 0.61 molar, which is going to be my concentration of my hydroxide ion. So then I take the negative log of that number. So if I take the negative log of the 0.61, sorry, I'm then going to get, and let me just plug that in, 0.214. So that's going to be my pOH. And now pOH is not where we stop. This is where a lot of people make a mistake, and they get in trouble. So they'll stop here and they'll say, okay, I found the pH. And it's like, no, you've actually just found the pOH. So what you're going to do is actually take 14 minus my pOH, which is what you just calculated, that's 0.21. And then you're going to get the pH, which in this case is 13.78. 13.78. All right, so please be careful on these. Make sure that you don't stop here, that you keep going. Okay, we're going to rank the following in recitation, so don't worry about that. We're going to go why these numbers descend and ascend in certain ways. Finally, write out the K value for the weak acids, and what is the relationship of the equilibrium constant K and Ka. So, when we're looking at the Ka equation, we're simply writing out the products, the reactants. The products are always going to be the dissociation products, so these will always have a H3O plus in them in the numerator, and then it's always going to have the A minus, so that minus a hydrogen, which we've seen before in recitation, so nothing too new. COO minus, and all of that is going to be divided by our acid. Now, when we relate this to our K value, we actually are just going to multiply this by water. Or specifically, you're going to take the equilibrium constant, multiply it by water to get Ka. Okay? So essentially, if I take K and multiply it by water, I would get Ka. Specifically, the concentration of water, because that is what is going to give us our K value, because most times water is what an acid is dissociating in. So that multiplied by K will also equal my Ka. Okay, we'll do the others in recitation. Finally, for the last one, 12. So when we're looking at 12, it says use an ice table. Well, I'm going to tell you how to not use an ice table for these, and the only reason I'm doing that is because I think ice tables confuse stuff. So when you're given a concentration of the acid and a pH, and you have to find the Ka, well, you're already given the concentration of the hydrogen, which we know is equal to the conjugate, the ClO minus, and you're given the concentration of H. So we can actually just write this out based on what we already know. And we don't even need to use an ice table. So Ka will equal the concentration of 10 to the negative 411 to give us our hydronium ion concentration, which will also give us our ClO minus concentration, which you get 7.76 times 10 to the negative 5. And again, because that is not only the concentration of our hydronium ion, it is also the concentration of our conjugate acid. In this case, we're going to square it, and then we just divide by the concentration of our acid, which is 0.15. All right, and when I plug that into my calculator, I get the dissociation constant, of 4.02 times 10 to the negative 8. Okay, now what if you have to find the pH of that? This is the same idea. So I'm just going to use the same formula, but I now have 1.8 times 10 to the negative 5, which is fine. And I know that I need to find this and the conjugate. So I have 10 to the negative 5 is going to equal x squared, because again, we don't know the acid because we don't know the pH, and we also don't know then the conjugate base. So this is going to be x squared. And then all of that divided by the concentration of our acid, which we know to be 0.3. Woo. .3, and then if I equal that together, I then just have to multiply this by 0.3 and take the square root. So the square root of x, which means that x is then going to equal, sorry, it's a little bit weird because it's got this funny cursor, is then x is going to equal 0.01 or 0.01313. Ooh. It keeps being weird on me. 13. Which then I know that I have to plug back in, so I just have to take the negative log of this, because again, we just found the concentration of our hydronium. So if I want to get pH, I have to take the negative log 0 of that, and then that means that I get a pH of 1.88. Great. All right, I will see you guys in recitation to go through the rest of that. Awesome.